Welcome to The Explainer. Today, we're diving into a core idea in mathematics that's way stricter and honestly way more interesting than you might think: the limit in the complex plane. So, what's our game plan? First, we're going to see why limits in two dimensions are a whole different animal. Then, we'll get into the formal rule they all have to play by. After that, we'll see what happens when those rules get broken. And they do. And finally, we'll connect all this abstract stuff back to why it's so incredibly important in the real world. All right, let's jump in. We probably all have some memory of limits from basic calculus, right? Well, you can kind of toss that out the window for a minute. Adding that second dimension, the imaginary axis, it completely changes the game. Think about it this way. On a regular number line, if you want to approach a point, you've only got two options. You can come from the left, or you can come from the right. It's like being on a single highway. But in the complex plane, it's like you're in the middle of a vast open field. You can approach your target point from the north, the south, from a diagonal. You can spiral in. There are literally infinite paths. And that creates a huge new challenge. So how on earth do you create a rule that works for an infinite number of paths? You need a definition that's rock solid, something that doesn't care which direction you're coming from. And here it is. I know, it looks like a bunch of Greek letters designed to be confusing, but hang in there with me. The actual idea behind this is way more intuitive and visual than it looks. It's really less of a formula and more of, well, a challenge, a game. Let's just reframe this as a game of target practice. Imagine someone challenges you. They draw a tiny, tiny target circle, we'll call it epsilon, around the point L, which is our proposed limit. Your job is to prove that you can always find a starting zone, a delta circle, around your approach point, z0, so that any point you pick inside that starting zone gets mapped right into the middle of their target. If you can always win this game, no matter how ridiculously small they make that epsilon target, then congratulations, the limit exists. Okay, and this brings us right to the heart of it all. That little epsilon delta game we just talked about, you have to be able to win it from every single direction. It doesn't matter if you come in on a straight line, if you zigzag, or if you spiral in. The outcome has to be the same every single time. So what happens if our map is wrong? What if one road takes you to the north gate of the city, but a different road takes you all the way to the south gate? The rule is simple and completely unforgiving. If even just two different paths lead to two different results, L1 and L2, then the whole idea of a single unified limit just falls apart. The limit does not exist, period. And this is the perfect function to show what we mean. We're looking at z conjugate divided by z as we approach 0. So let's try our first path, coming in along the real horizontal axis. The result, +1. Okay, but now let's try a different path. Let's come down the imaginary vertical axis. And what do we get? -1. So one path gives us 1. The other path gives us -1. Last I checked, those are definitely not the same number. The paths disagree. And because they can't agree on a destination, the fundamental rule is broken. There's only one conclusion we can make. The limit at that point does not exist. Game over. So why are mathematicians so strict about this? It's not just about being picky. This idea is the foundation for something incredibly important: continuity. It's how we determine if a function is well-behaved or smooth. The idea here is actually pretty simple. A function is continuous if the place it's heading towards, that's the limit, is the exact same place where it actually is, the function's value at that point. No sudden jumps, no gaps, no weird surprises. So for a function to be continuous at a point, it has to pass a three-part checklist. First, the destination has to exist. The limit has to be a real thing. Second, the point has to actually be on the map. The function needs a value there. And third, and this is the big one, those two things have to be in the exact same spot. The square root function gives us another fantastic example. Let's look at what happens as we approach the point -1. If we get there by arcing through the top half of the plane, our limit is the imaginary number I. But if we come up from the bottom half, we end up somewhere completely different, -I. Well, I and I are not the same, so the paths don't agree, which means the limit doesn't exist. And right there, we've broken rule number 1 for continuity. It's like there's a fundamental tear in the function at that point. All right, so why does all this abstract path disagreement stuff actually matter?
Because it turns out this strictness is the foundation for an entire branch of incredibly powerful mathematics.
This strict definition of a limit is the absolute bedrock for doing calculus in the complex plane. You literally can't talk about derivatives without it. In fact, there's a key theorem that says if a function is differentiable at a point, it is guaranteed to be continuous there. It's a one-way street, and it shows just how fundamental this idea is.
And this is not just some academic exercise. Complex analysis is an essential toolkit for electrical engineering, for physics, especially in fluid dynamics and quantum mechanics, and for things like signal processing and control theory. These strict rules are what make the powerful math possible. It's this level of rigor that lets us make these huge, sweeping statements. We can say with total confidence that all polynomial functions are continuous, everywhere. We know that rational functions are continuous wherever they're defined. It gives us a level of predictability that is incredibly powerful. So the big takeaway is this. Adding a new dimension forced us to be way more careful, way more strict. But it was that very strictness, that unbreakable rule that all paths must agree, that unlocked this whole new world of powerful mathematics. And it really makes you wonder, doesn't it? What other simple math rules that we take for granted get completely turned on their head when you step into the complex world?